Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. On. In this tutorial video, I'll go through this very recent March 2022. This is paper 1 variant 2 for the 9701 Cambridge International A-level exams. In this first question, so this is about first ionization energy. So we know first ionization energy is referring to, energy required to remove 1 mole of electrons from 1 mole of gaseous atom to form 1 mole of gaseous ion with a single positive charge. I mean, there are different definitions in different textbooks and different teachers, but if you're able to write these equations and you can be thinking about something kilojoule per mole of electron removed from 1 mole of gaseous atom to form 1 mole of gaseous ion with a single +1 charge, with a +1 charge, that would be all right, and you got all bits of the definition correct, right? So this is about potassium. When you think about potassium is period 4. Is the periodic table is now given in your actual question paper without a separate data booklet. So this is group 1. And then we see strontium. Strontium is below calcium. So it is in period 5, the 5th row in the periodic table. So it's in the 5th shell, and this is group 2. We would normally associate as you go down the group from period 4 to period 5, we're thinking about extra shell, and therefore these electrons are more shielded. But when we look at this value, it seems like it is actually more difficult to remove the one from strontium, to remove the valence electron from strontium, than to remove the valence electron from potassium. So this is pretty counterintuitive actually. So you got to read the value. You see, we expect going down, even though they are different group, we expect going down to a new shell, that these are further away, we expect to be more shielded. But this value is higher, so it is more difficult to remove, more difficult to ionize. This question is asking you, why? Why is it more difficult to ionize? So it cannot be due to shielding, because definitely with one extra shell, they're going to be more shielded. But why is it more difficult to remove? If it is not shielding, it has got to be down to nuclear charge, because we know in the syllabus, they said that we must explain in terms of nuclear charge, we must explain in terms of shielding, and we must explain in terms of sizes. So it's not shielding, it's not size, because they would have led us to being slightly easier to ionize. So it's got to be the nuclear charge, and therefore we're looking for not spin pair repulsion, not shielding. We are looking at the nuclear charge, so that is going to be A, because the charge inside the nucleus is due to the protons, and this is the only reason you can account for it, that will overcome shielding, and therefore the overall net electrostatic force attraction between your valence electrons and the nucleus is going to be stronger as a result. Question 2, this is about electronic configuration of magnesium ions. If you look at magnesium atom, so from your periodic table, your electronic configurations to, well, actually I was thinking about the O-level one. It should be 1s2, 2s2, 2p6, 3s2. So the magnesium atom will lose the 2 outer shell electrons. Now you get Mg2 plus ions. Having lost 2 electrons, now you have 2 extra protons than the electrons. You have 10 electrons here, you have 12 electrons there. So it's just a fully filled out the shell. It looks like neon electronic configuration. That's going to be option A there. Question 3, so this compound contains carbon, hydrogen, and oxygen only. This is the kind of question called combustion analysis. So very, very important. We can try and work backward, because this compound contains carbon, hydrogen, and oxygen. So when you combust them, when you completely combust them, you get carbon dioxide, water. Carbon dioxide is CO2, water is H2O. Complete combustion is in excess oxygen. Oxygen doesn't carry carbon or hydrogen, so that means all the carbon in carbon dioxide come from the carbon here. All the hydrogen from here come from here, but not all the oxygen are from here, because you have used excess oxygen, so some of the oxygen could have been from the molecular oxygen that reacted. So the first thing we need to do is find the mass of carbon inside the carbon dioxide. So out of 44, because the MR of CO2 onto your periodic table, you will get 12.0 relative atomic mass for 1 carbon. So 12.0 plus 2 times 16.0, so this gives me 44.0. And then for water, you get 2 times 1.0 plus 16.0, you're going to get 18.0. So overall, out of the whole 44.0, only 1 carbon is present. Therefore, it's 1 times 12 gram out of 44 gram per mole, and this is multiplied by 4.00 gram of carbon dioxide. So that means out of this 4 gram of carbon dioxide, what is the percentage composition? And therefore, we are not doing percentage, we are doing mass composition, so it's multiplied by 4 gram instead. So 12 divided by 44 times 4.00 gram, I get 1.09 gram of carbon. How about the hydrogen? We need to be very careful now, because this hydrogen, there are 2 hydrogens present in water. So there is 2 times 1.0, and this is divided by 18.0, and this is multiplied by 1.63 gram, because we have 1.63 gram of water. So the mass contribution from the 2 hydrogen, 2 times 1.0 divided by 18 times 1.63, I get 0.18 gram. Altogether, we know that the compound contains carbon, hydrogen, and oxygen. If we have the mass of carbon, we have the mass of hydrogen, we know the total mass is 2 gram. We don't know the mass of oxygen atoms. So the mass of oxygen atom is going to be your total mass minus the mass of carbon minus the mass of hydrogen. So 2.00 minus bracket 1.09 plus 0.18, I get 0.73 gram of oxygen atoms. These are the mass of the atoms. When you add them up together, you're going to get the mass of this compound, which is 2.00 gram. So they wanted to find the empirical formula, defined as the simplest whole number ratio of the atoms. So what I do here really is 1.09 divided by 12.0. This is called mole of equal to mass over AR, because it is about the simplest whole number ratio of atoms. Because we're dealing with atoms, we don't talk about the molecule. 1.09 divided by 12.0, I get 0.091. This is mole. This is 0.18 mole. And then 0.73 divided by 16.0, I get 0.046 mole, something like that. We wanted the simplest whole number ratio. So I don't know whether I'll get the whole number ratio or not, but the smallest number there is 0.046, and then 0.18 also divided by 0.046, and then 0.046 divided by itself. So that is just going to give me 1. So 0.091 divided by 0.046, that looks like 1.98. Give or take, that should be 2. And then 0.18 divided by 0.046, that is 3.9. So give or take, that should be 4. So C2H4O, this is the empirical formula. C2H4O, there's option C there. Now for question number 4, we're looking at dipole moment 0. So we're looking at non-polar molecule. So if you want a non-polar molecule, all of these are going to be tetrahedral, because they are carbons. They're only one carbon with 4 bond pair and 0 lone pair. So tetrahedral 109.5 degree. But then as soon as you have a different atom around your tetrahedral geometry, you're going to get a net charge distribution. You're going to get a net dipole, which make it polar. So when you have that, you want all the atoms in the tetrahedral geometry to be non-polar. So CH4 is non-polar. Anything in between, as soon as you have one atom which are not the same, so CH3Cl, CH2Cl2, CHCl3, so these 3 are going to be polar until you go back to having all 4 atoms that are the same, even though they are more electronegative compared to hydrogen, but all the 4 atoms are the same. If you do a vector diagram, as you do in mathematics and also physics in mechanics, so the vector diagram is going to close out and loop up onto itself, such that the net dipole moment will cancel out because they loop onto themselves, just like with CH4. When I said they loop onto themselves, what I meant is the resultant force is going to be 0, because dipole is a vector quantity. Vector has direction and magnitude. So if they close out onto themselves, the resultant is going to be 0. Probably I shouldn't call it resultant force. I should really call it resultant dipole, because that is the quantity there. So CCl4, just like CH4, is non-polar. Everything else in between is going to be polar molecule. Question number 5, we're looking at Al2Cl6. So this is a common thing. This is a dimer. You should really know how to draw the display formula first. So aluminium and aluminium, we have chlorine, chlorine, chlorine like this. So we've got empty shell. We got empty shell because the aluminium is in group 13. It's got, empty orbitals because it has only 2, 4, and 6, 2, 4, and 6 around each aluminium. Around each aluminium, there's 6 valence electron. So coincidentally, this neighboring chlorine has lone pairs, and this can donate both the electrons onto this empty orbital. Electron pair donor, electron pair acceptor. It's got lone pair electron, it's got empty orbital, whereas this one will go to the other side. So you can think about it, about this molecule being rotated around as well. So it could be going this way and then this going that way. It's the same as that if you mirror these, like if you flip 120 degree from front to back. So we're looking at these two being special bond. These are called dative covalent bond, or you will call them as coordinate bonds, and you will see more of these in A2 transition metal chemistry, although this was covered in AS chemistry obviously. So the electrons from chlorine are the dots, so we can see that these are our 2 dots there, they are our dative covalent bonds, and as a result of it, you're left with only 4 electrons which are non-bonding. You only have 2 lone pair there, and you only have 2 lone pair there, so the bond angle there is going to be 104.5 degree because you have 2 bond pair and 2 lone pairs, just like in water. Whereas here, the aluminium is going to be 109.5 degree because it's got 1, 2, 3, 4 bond pair and 0 lone pair on each of the aluminium. And because this thing, the chlorine on the outside don't form dative covalent bond, they're still going to have 3 lone pairs around each chlorine as such. So the rest of them are wrong because we are looking at Al2CO6 being a simple covalent molecule and not ionic as shown in option A there. As for Y, C, and D are wrong. If you see here, the aluminium has formed a covalent bond. This is going to be the one which is a wrong concept there. And as for Y, the other are wrong. If you count the crosses, if you see the electrons from aluminium, you will see that you have original 1, 2, 3, and 4. So you're looking at 4 electrons from the aluminium. So I'm showing the other one. Aluminium is in group 13. If you look at your IGCSE or O-level curriculum, group 13 has got 3 valence electrons. If you want to do the A-level style electronic configuration, I could start from neon, and then I would have 3s2, 3p1. So 3 electrons in the outer shell as well, like that. Question 6, this is about boiling point. This is about hydrogen halide. Hydrogen halide is not like hydrochloric acid, hydrobromate. Instead, it is a simple covalent molecule, which I can draw dot and cross, like this, because the group 17 element has 7 valence electrons. So if I write this as, I don't know, if I write it as Y instead of X, so that to avoid confusing with the dot and cross diagram, I would have 6 electrons left around the Y because I only use 1 electron for bonding. So HCl, HBl, HI, these are all simple covalent molecule. So if we have simple covalent molecule, we have simple covalent structure, which means when we boil simple covalent molecule, we are breaking the weak intermolecular forces between the molecule. This is specifically talking HCl to HI, so we are not talking about hydrogen bond, because hydrogen bonds, you need a very polar bond. In fact, you get very polar bond when you have hydrogen bonded to F, nitrogen, or oxygen. These are the 3 most electronegative elements, and you don't have the HF here, so we automatically don't talk about hydrogen bonds. We don't talk about the bond polarity from HCl to HI as well, because if you think about electronegativity, chlorine is more electronegative than bromine than iodine. So if I have my hydrogen there, you can see that HCl is the most polar. If you look at the difference in electronegativity, based on the difference in electronegativity, you can tell HCl is the most polar. And if HCl is the most polar, HCl should have the strongest permanent dipole, and HCl should have the higher boiling point. But it's the opposite trend. So the intermolecular forces get stronger. That is why we need more energy in order to overcome the intermolecular forces. So it can't be due to the increase in bond polarity, because the bond is actually becoming less polar, going down group 17, if you follow that particular simple line diagram which I've drawn, not to scale, just to show the representative effect. In terms of the bond energy, that is definitely wrong, because we do not break covalent bond. We are not doing we are not doing thermal stability. We are talking about boiling point. So we are just breaking the weak intermolecular forces. So the strength of the intermolecular forces of attraction is getting stronger, and that is to do with the van der Waals due to the greater number of electrons. So your total number of electrons in the molecule is going to be higher. And as that increases, your van der Waals will get stronger, but do not forget that also the surface area of the molecule also increases. Therefore, your van der Waals are getting stronger. That's option B there. If you don't like to use the word van der Waals, I think you can use induced dipoles, London dispersion forces as stated in the new syllabus. Question 7, this is about Pauling electronegativity values. So you're given these particular values, which of course you're not expected to know what they are. So which row put these substances in order of increasing melting point? So what can we say? Well, first of all, what can we say actually? If you look at the difference in electronegativity, if I put in on a scale here, E and let's say I have Z here, so this is the highest, and then I have Y, and then I have X. So in terms of the largest difference in electronegativity, is going to be between X and Z. So X and Z has the largest difference in electronegativity, as you could see there. And then you have X and Y, which is the second largest in electronegativity there. When you have things like Z and Z, so this is going to be very electronegative element, so the most electronegative out of the three. So this is with itself, they are going to be as a molecule. This is going to be simple covalent molecule, so it's going to be non-polar because they are bonded to themselves, they have the exact same electronegativity. In terms of the lowest melting point, we're looking at the non-polar, and this has to be simple covalent molecule. So Z2 and Z2 is going to be the lowest melting point there, which means C and D could be our answer, but not A and B. In terms of our highest melting point, we think about the difference in electronegativity. The smaller you are, well, they're not looking at XY, they're looking at YZ. If you have the bigger electronegativity difference there versus between this and this, we're going to say the bigger difference. Well, you can think about polar, but you could also be thinking about the extreme of bonding, where instead of, being very polar, you could also get ionic bond. How do I know it's ionic bond? I don't know. At this point, we're just looking at values. So between 4.0 and 1.0, very electronegative non-metal, less electronegative, very electropositive metal. So they like to transfer electrons from the metal to the non-metal, where this will like to gain the electron, this will like to lose the electron. When you get ionic bonding, get ionic compound with giant ionic structure, and they will have very, very high melting point as compared with, breaking the weaker intermolecular forces between YZ molecule, for instance. Okay, so between the two melting points, I would think that the higher electronegativity difference would tip the balance more towards ionic bond and less of covalent bond, and therefore less simple molecular and more of the giant ionic structure. So XZ is going to have the higher melting point as a result. Question 8, we have a reaction that shows, well, actually it's like fermentation, isn't it? Which you had done in IGCSE or O-level chemistry. You started from sugar, and then you get some biofuel. This is your biofuel, which is basically ethanol as we know it. And then this is your carbon dioxide. So it's not combustion, it's just producing carbon dioxide and biofuel, which is ethanol. So we have enthalpy of combustion. The enthalpy change when you combust, when you burn 1 mole of a substance, is in kilojoule per mole when you burn 1 mole of a substance. And this is in excess oxygen. Everything in standard states, under standard conditions. So what we have there is we burn 1 mole of sugar and we produce 2 mole of carbon dioxide. Carbon dioxide doesn't combust, it's a product of combustion. So carbon dioxide have an enthalpy of combustion of 0, which is why they don't give you, and you're not supposed to look for it because you're supposed to know it's 0. Carbon dioxide does not combust. I mean, we use carbon dioxide to put out fire, right? So we also produce 2 mole of ethanol. When you think about enthalpy of combustion, you have reactants going to products. And then these are enthalpy of, well, this is enthalpy change of reaction. But when you think about combustion, you can get combustion products. So the arrow is coming down because that is your enthalpy of combustion of your product. This is your enthalpy of combustion of your reactant. Remembering that enthalpy of combustion is for 1 mole of a substance. So, when we look at Hess cycle, enthalpy change of a reaction does not depend on which path you take. So you can take the indirect route, and I can get the formula delta HR is the sum of the enthalpy of combustion of reactant minus the sum of the enthalpy of combustion of product. If you follow the arrow there, Hess's law, coming down in the same direction, so it's plus. Going against this direction, so it's minus the combustion of the reactant. And do not forget that this formula also represents the sum and not just individual value. Looking at your reactant above, we are given the combustion of the sugar, which is just A, and then we have minus, and we're producing 2 moles of the products. So this is 2 times the enthalpy of combustion of the product. This is 2B. So A minus bracket 2B is A minus 2B. That's going to be option D there. Question 9, nitrogen monoxide is an atmospheric pollutant. So you produce this when you have this nitrogen, very strong triple bond reacting with oxygen gas in the air. And this is a result of your car engine having very high temperature, because when you start car engines, you need to overcome the activation energy, and the activation energy of the nitrogen bond being broken has been overcome by that reaction, which is very similar to what happened when you have a lightning. Enough electricity from that bolt of lightning in order to break the nitrogen strong triple bonds in the atmosphere. So we're looking at endothermic reaction. So this means delta H is greater than 0. That means the reactants absorb energy. So the energy of product is higher than the energy levels of your reactants. Your delta H is going upward. This is correct. Your delta H is not really correct there, because it should be from reactant to product. It should be from reactant energy level to product and not the other way around. Our enthalpy change here is lesser than 0. This is for exothermic reaction. This is for endothermic. So we're left between A and D. In terms of activation energy, it's from the starting energy level of the reactant to the top of the peak. So very clearly A is our answer there. And why is D wrong? Oh, D is wrong because that is not supposed to be endothermic. I beg your pardon. Again, for the same reason, from reactant to products. So, not from products to reactants for the forward reaction. So A is our only possible best answer there.